The textbook that you have does not cover this per se, but I did make a copy of an addendum that's added to your textbook that was, I think it was actually written by someone from the University of Pittsburgh to kind of put onto this course using the Axler textbook in order to come up with more things we do with complex numbers. And it's going to discuss Euler's formula, which allows us to do some things with complex numbers involved that we weren't able to do with real numbers. Like, for instance, we're going to be able today, after this point, to be able to do logarithms of numbers that we couldn't do beforehand. So we kind of get into that and show how that could possibly be done. So, one of the first things they teach you in this addendum is that there's a second polar form for a complex number. And essentially, it's just basically taking one more step in that process. We learned how we could take a complex number and put it in terms of cosine t and I times the sine of t. It's usually multiplied by some modulus. Well, that portion of it, the cosine t plus I times the sine of t, can also in turn be written as e to the it power, where I is, of course, a complex number, I, and t is a real number that, was ended up being the angle we were taking that sine and cosine of. So if I wanted to find polar representations of the following written in this new polar format, I would still go through the same process I did before for do the polar representations. First, I would, say, well, 2 equals 2 times the quantity 1 plus 0i. Because remember, it's just 2 times 1, and 1 plus 0i is 1. The reason why I'm doing that is that, a simple real number or a simple imaginary number is going to have a modulus that goes along with the number you usually just have in front. When you get those two-termed ones like we have in D, the two D's, I don't know why I have it D and D instead of D and E. But, excuse me, it gets a little bit more complicated to figure out what the modulus is and what you're going to factor out. But we're going to talk about those when we get to it. Now, in order to put this more into polar form, I look at this and say, okay, well, I'm looking for an angle theta or t, whichever way you want to call it, that when I take its cosine gives me 1, and when I take its sine gives me 0. I could say 0 for that, but we try to avoid the 0 because, especially since if I do that, I'm going to have e to the I 0 power, which just isn't going to help me out at all. So I'm going to put 2 pi there because 2 pi is, after all, coterminal with 0. And the fact that I have coterminal angles involved kind of leads us to some of the things we're going to talk about momentarily. So I could turn this into 2 times the cosine of 2 pi plus I times the sine of 2 pi, which according to this new thing we learned up there, that cosine of 2 pi plus I times the sine of 2 pi could all be turned into e to the 2 pi I power. So I could write the number 2 in polar form as 2e to the 2 pi I power. For b, 2i, that's going to be 2 times 0 plus 1i. Of course, an angle that has a cosine of 0 and a sine of 1 would be pi over 2. So this becomes 2 times the cosine of pi over 2 plus I times the sine of pi over 2. And of course, all of that inside the parentheses becomes e to the pi over 2i power. Negative 2, still going to have a modulus of 2. But it's 2 times the quantity negative 1 plus 0i. I'm looking for an angle that has a cosine of negative 1 and a sine of 0. And of course, pi is the number that does that. So it becomes 2 times the cosine of pi plus I times the sine of pi. And all that stuff in the parenthesis, according to this new rule, I'm allowed to rewrite that as e to the pi I power. 1 plus I. Now here I have to calculate what the modulus is. And I don't show the calculation, but I would take, use the Pythagorean Theorem on the a and b values, both of which are 1, so I get the square root of 2, which I do factor out. And if I factor that out, I get the square root of 2 times 1 over the square root of 2 plus 1 over the square root of 2i. Now, 1 over square root 2, square root 2 over 2 are the same numbers, so I got to think of what angle gives me a cosine of 1 over the square root of 2 and a sine of 1 over the square root of 2. Well, that's pi over 4. So it's become square root 2 times cosine pi over 4 plus I times the sine of pi over 4. And of course, according to this new rule we have up here again, let's see if I get this thing right up here again, that's going to become the square root of 2 times e to the pi over 4t, pi over 4I power. Sorry, I said t for a second. Negative 1 plus I, again, I have the a value being negative 1, the b value being 1. If I calculate the modulus r, it's square root 2, which I do factor out. I end up with square root of 2 times the quantity negative 1 over square root of 2 plus 1 over square root 2i. So I'm looking for an angle that has a cosine of negative 1 over the square root of 2, but a sine value of 1 over the square root of 2, and an angle that does that is 3 pi over 4. So square root 2 times cosine of 3 pi over 4 plus I times the sine of 3 pi over 4, which I could then simplify a bit further and say that's the same thing as the square root of 2 times 3 pi over times e to the 3 pi over 4 I power. I put it in front here again. We oftentimes will do that in order to make sure that, you know, I'm not putting something underneath the radical that's not supposed to be there. So if I want to make sure I don't mistakenly write it in a way that makes people interpret as though it's underneath the radical, I make sure to put it in front so there's no miscommunication there. So that's the new polar form we talk about when we start talking about Euler's method. Now it says find Cartesian representations of the following. So here's just kind of reversing the process. E to the I pi power means I'm going to have the cosine of pi plus I times the sine of pi, which is going to be negative 1 plus 0i, which is negative 1. So that's what it is. E to the 3 pi I power is going to be cosine 3 pi plus I times the sine of 3 pi, which also gives you negative 1 plus 0i, which is equal to negative 1. So we can see that we have two different powers of I that look like very different powers of I, but they're the same thing. That's because pi and 3 pi are coterminal angles again. And that coterminal angle issue is going to create a circumstance when we start dealing with logarithms that we're not used to seeing for logarithms, but in complex numbers, and something's going to happen as a result. Sometimes they'll give you some challenging ones. I think this was pulled off of a web work problem. So I want to be able to write pi to the 2 plus I power, which is I squared times pi to the I power. Pi to the I power is what I'm going to have to convert around a little bit because, you know, pi squared is just a number, okay? Now, pi to the I have to start, I mean, the only way I usually go from a, you know, complex number where I have I in the exponent to one where I have it in standard form is for me to get e involved. So I'm going to call this number pi to the I power e to the natural log of pi I, because if I have that e and natural log in quick succession of each other, they would normally just cancel each other out. So I put two inverse functions in there that would cancel out, and therefore I'm not changing the value of it. But what I am able to do with this, of course we're writing it like that because if I take a log of something raised to a power, I can move that in front. And so I have e to the I times natural log pi, where natural log pi is my t value. So this becomes pi squared times cosine of natural log pi plus I times the sine of natural log pi. Which means if I distribute the pi squared, I'm going to have an a value that's pi squared cosine of natural log pi. Now that would be a number. It's not going to be a very rational number, but it's going to be a number. And I have my b being pi squared times the sine of natural log pi. So, and that would be the way I would express the number. I mean, I could, at that point, get approximate values. But, you know, generally, that would be the number that I would get if I took e to the 2 plus, or pi to the 2 plus I power. Just want to see something with that. Yep, that's what I would get. So, and again, your calculator could check a lot of these answers for you in the long run. So, but you have to show the way how you would get there. Because we're changing formats here. This question is asking us to see like how will we express a complex conjugate in terms of having this, everything in terms of e here. And so what they're telling you here is that e to the I theta and e to the negative I theta would be complex conjugates for any real value of theta, which means that any angle measurement. So I start with e to the I theta power, and based off of the rules we learned in this beginning of this lesson, that's going to equal cosine theta plus I sine theta. When I do a conjugate of that, all I'm going to do is change the sign and make it cosine theta minus I sine theta. Now here's where I'm going to start working with some identities. I know that I can put this to say that cosine theta plus I times negative sine theta. I know that cosine of negative theta equals cosine theta. I know that the sine of negative theta is negative sine theta. So I can actually do a replacement here and say this cosine theta plus I times this negative sine theta is the same thing as me having cosine of negative theta plus I times the sine of negative theta, and then reverting it back into a format that has e in it. I would have e to the I times negative theta power, which is e to the negative I theta power. So that proves more or less that these two numbers would be conjugates of each other. So if I would see any complex number represented in this polar form, it is a polar form, and I would see like for instance e to the 3 pi I and e to the negative 3 pi I, they would be conjugates of each other. They'd be complex conjugates. Here we want to show that if I take if z is a complex number, if I take e, raise it to a complex number power, and then take its absolute value or modulus, it's just the same thing as me taking e and only raising it to the real number portion of that complex number. More or less saying that taking e and raising it to an imaginary number and doing its modulus doesn't do anything. It's actually, that value is basically nothing. So let's have a look at this. I'm going to let e to the z equal, of course, e to the x plus iy power. Which means that that's the same thing as having e to the x power times e to the iy power. According to what we just got done doing with the formulas here, e to the iy power would be the cosine of y plus I times the sine of y. Okay, so e to the z now equals e to the x power times the cosine y plus I times the sine of y, because that was in terms of I. Now I'm not looking to do the e of z, I'm looking to do the absolute value of that. So I'm doing the absolute value of all these things. When I do the absolute value of a product, okay, e to the x power is going to be positive, and because I know that is the fact, I can actually separate these into two separate absolute value problems, because I know that e to the x power is going to be positive regardless of what x is. So I have the absolute value of e to the x equaling the cosine of y plus I times the sine of y. Well, since I know that e to the x power is going to be a positive number, I can also say that the absolute value is going to have no effect on it. As far as the absolute value of cosine y plus I sine y, when I do the absolute value of a complex number, its modulus, I just apply the Pythagorean theorem. So I'm taking the a portion, which is just, give me a second here, this portion here, and the b portion, which is this portion right here, and I'm doing the Pythagorean theorem on it. So underneath that square root, I have cosine squared y plus sine squared y, but that's also a Pythagorean identity. Cosine squared of an angle or a value plus sine squared of that same value just equals 1. And of course the square root of 1 is 1. So I end up with e to the x times 1, which is just e to the x power. So it's proven. The QED is just an abbreviation for the Latin words that means it is accomplished. Don't ask me what the Latin words are. I never studied Latin. I don't remember it. I just asked once, and I remembered what they said as far as what it stood for, except the actual words I don't know. Let B be any positive real number. What is the value of the absolute value of b to the I power? Which basically says that, if I take any real number, raise it to the I power, and do its absolute value, what does it become? So, well, first, we have a way of converting to things that I could have, because I want to try to get this in terms of a complex number when all is said and done. B to the I power, if I have a real number, which is a complex number, being raised to I, which is also a complex number, I should expect to have a complex number as a result. I want to be able to write that in its standard complex number format. And the only way for me to go from anything that has an exponent with complex numbers in it to a standard complex number format, I have to get e involved. So I'm changing b to the I power into e raised to the natural log of b to the I power, because again, putting e and natural log in quick succession of each other would normally cancel them out. Usually if I had this, I would just say it's b to the I power, but I want these two involved so I can start using Euler's formula in order to accomplish more with this. So, using the power property of logarithms, I can move that power of I in front and make it a multiplication. So I have e to the I natural log b power. Because I do now have a power of e where I have a real number times I can now change this into the cosine of natural log b plus I times the sine of natural log b. Again, I'm doing absolute value of these things. So when I have a complex number now, even though it's more in a polar format, I still have a complex number. When I perform, do an absolute value, I'm going to perform the Pythagorean Theorem on it. So I end up with the square root of cosine squared of the natural log of b plus the sine squared of the natural log of b. Which means that by the Pythagorean identity, the cosine squared of natural log b plus sine squared of natural log b would equal 1. So the square root of 1 is just 1. Which basically says if I take any number, raise it to the I power, and do its absolute value, it's going to equal 1. Doesn't matter what the real number is. So, this is more of a review of what we talked about in the last lecture, except in the last lecture, most of the time when we were doing situations like this, we were doing, find all the cube roots of a real number like 3 or 8 or -2 or something like that. Real numbers. Here I'm doing definitely a complex number or an imaginary number. So we're looking to see, we want to let z cubed equal I, and I in polar format is going to be this. And we talked about things like that before. Like I could write as 0 plus 1i. It has a modulus of 1, so I don't have to worry about that so much. An angle that has a cosine of 0 and a sine of 1 would be pi over 2, and that's where that comes from. I don't turn this into the e format because when I do roots of complex numbers, I still want the polar format so that I can use De Morve's. I already forgot how to pronounce it. De Morve's theorem, which basically says that if I want to do the root of this to figure out what z is, I'm going to do the cube root of 1 times the cosine of the original angle pi over 2 plus 2k pi all over 3, which is the root number, plus I times the sine of pi over 2 plus 2k pi all over the root number 3, where k equals 0, 1, and 2, because we always start at 0 and then 1 less than my root value number, which is what we call n. So, if I let k equal 0, z is going to equal, the cube root of 1 is 1, so I'm going to have 1 times the cosine of pi over 6 plus I times the sine of pi over 6, which are, of course, values I do know. I should know the cosine of pi over 6 and the I times the sine of pi over 6. And these kind of things are going to happen a lot in these last few lessons in Chapter 6, as of course you haven't noticed, where I do have my special angles show up, or situations where I have to know my special angles are involved. So if you don't know your tables of trigonometric values for your special angles by this point, you're going to be in a whole world of trouble. So make sure that if you haven't gotten to a point where you know them very well yet, keep working on it, because it's gonna really start hurting you if you don't. Because the cosine of pi over 6 is the square root of 3 over 2. The sine of pi over 6 is 1/2, so I have the square root of 3 over 2 plus 1/2 I, which is in the standard format. So if k equals 1, I'm going to have z equals, of course, the cube root of 1 again is 1. If I take pi over 2 plus 2k pi, I end up with 5 pi over 2, and divided by 3 gives me 5 pi over 6. For the angle, of course, the cosine of 5 pi over 6 would be negative square root of 3 over 2. The sine of 5 pi over 6 would be 1/2 again. So I end up with negative square root of 3 over 2 plus 1/2 I for this one. Notice they are not conjugates, because the plus sign between the two numbers didn't change. It was the signage of a that changed. And of course, for k equals 2, again, the cube root of 1 is 1. If I take pi over 2 plus 2k times pi, or in this case 2 times 2 times pi, I end up with essentially, what was it? No, give me a second here. Ooh, it's one of those bad days. That's going to be 4 pi. I'm going to end up with 9 pi over 2, which becomes 9 pi over 6, which simplifies to 3 pi over 2. And so I end up with the cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. The cosine of 3 pi over 2 is nothing. The sine of 3 pi over 2 is negative 1. So I'm going to end up with negative 1i, or just negative I. And those are the three values that if I cube them, will give me I as an answer. Exercise 7 here. Let z be a non-zero complex number. A complex number w is a logarithm of z if e to the w equals z. So based off of this premise, show that every non-zero complex number has infinitely many logarithms, and find a recipe, same thing as a rule or formula, for calculating them. So one of the first things we're learning here is that, up to this point, we've only dealt with doing logarithms of positive real numbers, because that's all we could do. Now when we go into the complex number system, we can start doing logarithms of negative numbers, because they're complex numbers, and we can start doing even logarithms of things involving I. So, we start opening up what those are going to be, but the thing is, when we open that up, we also are leaving the possibility of having an infinite number of possible logarithms. And let's show why that happens. So we're told that e to the w equals z, which means that z can be written as cosine theta plus I times sine theta, which is e to the theta I power. Okay, so we're letting w be theta I here, so to speak. Okay. And if I do the natural log of e to the w power, which equals the natural log of z, which equals the natural log of cosine theta plus I sine theta, that's going to equal the natural log of e theta I. And I get some simplification here. But the thing is, the cosine of theta plus I times the sine of theta, because that's how we bridge this gap. That's how we go from a complex number into something in terms of e that I could take a natural log of. Is this bridge here, this cosine theta plus I sine theta. The thing is, if I take each theta and add 2n pi to it, I get another theta that puts me in the exact same position, being coterminal, that, in such a way that, it's going to be the same value. So that means that w can actually be the natural log of cosine of theta plus 2n pi plus I times the sine of theta plus 2n pi, which means, since n could be any integer, that w could be theta plus 2n pi I. So, so if I get like an instance where, if I'm solving something like this and I do a logarithm and figure out what w is, and w ends up being like, I don't know, pi over 6. Well, if I add 2n pi to that, and get 13 pi over 6, that would also be a value of a logarithm for that exact same number. So I have to. So that's why I end up with an infinite number of answers, because since we're involving these trigonometric functions, and trigonometric functions repeat in value for coterminal angles. That's why I can have an infinite number of angles that have the exact same sine and cosine pairing, and because of that, I can have an infinite number of things that would have the exact same logarithm. So when they say here, find all of the logarithms of -1. Well, -1 could be written as 1 times -1 plus 0i. Now again, I'm writing the 1 on the outside to show a modulus. -1 plus 0i, well, a number that gives me -1 for cosine and 0 for sine would be pi, so I can write this as cosine pi plus I times the sine of pi, which equals e to the pi I power. And so if I wanted to do the natural log of -1, I would do the natural log of e to the pi I power, and I would get pi I as one of the possible solutions. The thing is, though, -1, based off of what we're talking about here, can also be written as the cosine of pi plus 2n pi plus I times the sine of pi plus 2n pi, again going with the whole idea of coterminal angles. So essentially, that would give me this, which means that the natural log of -1 would be the natural log of this thing here, which would be pi plus 2n pi all times I. Or I could write it as 2n plus 1 pi I, which basically means pi I, 3 pi I, 5 pi I, negative pi I, negative 3 pi I, negative 5 pi I, negative 7 pi I, and all the way down both directions are all answers that would go along with the natural log of -1. Now, on your calculator, you will not be able to compute the natural log of -1. I think even if you have a complex mode on your calculator, you get away with it. Some have them, some don't. But when you get into that, if you put it into a complex mode, which you do have the ability on most TI-84 calculators of doing that, and if you want to be able to figure out how to do that, let me know. We could bring it up in class and we could talk more about that. But that's just basically allowing complex numbers to be given, but then everything's written as a complex number, and that gets to be a pain in the butt to leave it that way. If you have it in your standard real mode, it's not going to work, but if you actually, say, if I take e to any one of those powers down here, pi I, 3 pi I, 5 pi I, 7 pi I, I'm going to end up with -1 as an answer. So that's another way of checking to make sure that your work is right. So, keep that in mind about ways of checking the work, but you do have the ways of doing that on your calculator. Okay. Sometimes you get, we talked about sinusoids before, which are just basically, what a sine curve looks like, and many sinusoids could be written in terms of sine and cosine. Sometimes you get some sinusoids that, it's hard to distinguish what, the actual phase shift and amplitudes and baselines and things are, because, they're not placed in good spots. They're not you don't have maybe you have a baseline that itself is an irrational number, so it gets hard to measure. How far up and down you're moving. Sometimes you may have a period that's not really suitable for the graph you have in front of you, so you really can't tell how to scale the graph to get a better indication of what that period is and things like that. So some of these sinusoids are produced when you have situations where you have two different sinusoidal functions working in conjunction with each other. And in those kind of situations, to figure out the periods and phase shifts and things like that could be kind of tough. So they figured out that using some complex number theory, you can actually get the information about a sinusoid a lot easier, because if you calculate what they call a phasor, and the constant a e to the, trying to think what that is there. I think that's I phi power. Kind of works the amplitude and phase shift into one thing. So if you have that phasor and then use that phasor, which is going to be a complex number, and figure out based on the complex, plotting that complex number on a complex plane and figure out the polar coordinates from that. And that's where this things get really confusing, because we're doing a polar form of a complex number. Then we're taking a complex number, graphing it, and finding its polar coordinates, which is not the same thing. So there's a lot of things that, you know, sound a lot alike, but are not the same thing, working in conjunction with each other here. And that's where some of the confusion gets sometimes caused with this. Now, I go over this only because of the fact that, one, you do have a web work problem exactly like one of the problems we're going to go over here momentarily, talking about phasors. And that's the only reason why I'm going through it. I wouldn't give you something like this on a test or a quiz, because the process of doing so could take a bit of time, especially if you're new to doing it. And, you know, I could give you a quiz item, but that'd be the only thing you would do on the quiz. You know, there's other things I want you to be able to do on a quiz and on the test involving Euler's formula and de Moivre's theorem and formula as well. So, but this was all in the reading that you were given in that addendum series, so I'm not going to repeat it all. Let's show how these things could be used. So, first thing is find a phasor of the sinusoid 5 cosine 3t plus 2. Which basically means, from this, if I wanted to calculate essentially, the amplitude and phase shift, I could say this one has an amplitude of 5, a phase shift of negative c over b, which would be a negative 2/3. I should be able to get that, those two values from the phasor if I wanted to, when all is said and done. But here's how I go about calculating a phasor. First of all, I take the function f of t and I create another function, capital F of t, where I basically have the same original function plus I times the same thing with the trig function of sine instead. That's what they talk about, having the sine function when it's slightly out of phase. If I have it in this format here, this is what's going to start letting me put it in terms of e and things like that. So that's what I'm looking to do here. Because I'm going to turn this into 5 times, I can factor out the 5 and have 5 times the cosine of 3t plus 2 plus I times the sine of 3t plus 2, which according to what we've learned in this particular section, I can rewrite this as 5 times e to the 3t plus 2i power. Since I do have an addition in there, I'm going to distribute the I, so that gives me 5 times 3t to the I power times 2i. And if I rearrange it, I have 5e to the 2i power times e to the 3ti power. The phasor is the part that's all number. If I have e to the 3ti, that's where I have a variable, so the phasor is this thing here. And if I put it back into standard form, I would have this. So that complex number essentially is the phasor. Now, the fact of the matter is, as I said before, this incorporates both the amplitude and the phase shift in a single complex number. Because when I look at, for instance, the amplitude, if I want to figure out what the amplitude is, the amplitude would just be essentially the absolute value of this. So if I did negative 2.0807 squared plus 4.5465 squared and square rooted that, I do get about 5. Now, I'm off a little bit because of the fact that I did some rounding. And because I know that this number here, this complex number in a complex plane, I'd be writing it in this direction here. Like so. I should be able to figure out, what theta is. This is alpha here, which I can figure out, and this is what theta is, or t, or whichever way you want to call it. That's going to be what my phase shift is. So essentially, I know that alpha, if I just ignore the negatives, I mean the 4.5465 would be my numerator in a tangent function. The negative 2.0807 would be the denominator. If I do the arctangent of that, I get about 1.141599999. Now that's what alpha would be, and if I do pi minus that, I get a phase shift of 2. Which I can kind of see, here's the phase of here. I see that plus 2 up here again. So, I mean, that's coming from the same whole idea. I mean, it's kind of putting the phase, not the phase shift, the phase. The phase shift is like negative c over b. They often call this number here just the phase. So that's what they're trying to get at in that whole explanation. So that's how you calculate a phasor. The question you're asked to do in web work is similar to what I have here in example 10. So if you graph this sinusoid, 2 cosine 3t minus 4 sine 3t, you would get it looks like it's a regular sine curve. It's pretty small, and it's really hard to determine, what the period is and things like that just by counting it off, okay? What we want to be able to do is figure out, what this would be in terms of, cosine only. Because if we could do that, then we would be able to figure out the amplitude, the baseline. The baseline looks like it's going to be 0 still, but what the phase shift is, what the period is, all those things we need to know if we put it in terms of one trig function. We have 2 trig functions interacting with each other, that gets a little more difficult. So what I want to do here is I have 2 different functions going. I have f of t and I have g of t. And each one of these I'm going to employ that method. Now the thing is, when I do that conversion from f of t to capital F of t, I can do that pretty easily because I have it in terms of cosine. The problem is that g of t currently is not in terms of cosine, and that process only works if the original function's in terms of cosine. So for g of t, I'm going to use the fact that the sine of theta is equal to cosine of theta minus pi over 2. So I'm going to turn g of t into negative 4 times the cosine of 3t minus pi over 2. The whole idea about that, the whole idea behind that premise is that, if I just move a phase shift to pi over 2 away from, an angle, I'm going to be in the same position, for cosine as sine would be. So now I can rewrite these as capital F of t and capital G of t, where basically I have, the cosine of the original thing I have in the function, and then I have I times the sine of that same angle. Of course, when I employ the new formula, Euler's formula, saying that, cosine of 3t plus I times the sine of 3t is going to be the same thing as e to the 3t I power. Same thing with the cosine of 3t minus pi over 2 plus I times the sine of 3t minus 2. I'm going to end up with e to the 3t minus pi over 2 I power. Of course, the negative 4 and the 2 just kind of come along for the ride. And I want to figure out the phasors of each one of these. So for capital F of t, the 2, because the e to the 3t I power is all, the expression part of it. That's the part that's always, I should see in each one of these 2 things. Anything that's on the outside of that is just going to be my phasor portion. For capital G of t, I have to do a little bit more manipulation because I do have 2 terms in my power of e. So I'm going to have negative 4 times e to the 3t I times e to the negative pi over 2i, which gives me negative 4e to the negative pi over 2i times e to the 3ti, which means the phasor portion is negative 4 e to the negative pi over 2i, which I then convert into a standard complex number, which eventually, for the work you see there, becomes 4i. So the actual phasor for the left-hand side is the combination of these two together. So the actual phasor is the number 2 plus 4i. Now again, since I'm looking for the amplitude and I'm looking for the phase, the number that I have going next to the being added to the 3t, I do this again by first the a is calculated by me doing the absolute value of this. So I have the absolute value of 2 plus 4i. Again, I'm just going to employ the Pythagorean Theorem. I end up with 2 times the square root of 5. Now, the reason why I can say phi is automatically the arctangent, because in this case here, if I drew a graph of this, 2 plus 4i would be going in this direction. So if I calculated alpha, that would be the same thing as the angle I'm looking for here. If I was looking for an angle that a complex that would put me in some other quadrant, I would calculate alpha and then use that to help me find what phi is. But here I know that the arctangent of 4 halves is 1.01715. So now when I put this in terms of the final answer, writing this in terms of cosine only, I could say that 2 cosine 3t minus 4 sine of 3t is approximately equal to 2 times the square root of 5 times the cosine of 3t plus 1.10715. Or I could just say 3t plus the arctangent of 2 if I wanted to be more accurate. So, and that would be it. If I graphed either one of those two things, they would go right over each other. So, and that's what I was looking for. If you have any questions with these, please make sure to bring them with you. Along with that, make sure you do the practice questions. Again, the example 10 was there to help you do the problem that's on WebWork as it is. Most of the questions that I have as follow-up to this is kind of the questions that show up more along the lines on quizzes and tests that I'm going to ask of you to be able to do. So be sure you do those problems and have any questions about those or any questions about this lecture when you come to class after this. After this, we have one more topic to discuss, which are limits. And after we're done with that, we're going to start reviewing for the final. So until the next lecture we're together, I'll see you around. Bye, everybody.